Welcome to Electronic Specify Insights, the podcast for electronics engineers. I'm your host, Paige West. In today's episode, I speak with Matthias Huber, Senior Director and Solutions Manager for IoT, Embedded and Edge Computing at Supermicro. The discussion centres around a white paper co-authored by Supermicro and NVIDIA, which examines how predictive and generative AI can be adopted at the edge in sectors such as manufacturing, healthcare and retail. Matthias outlines key considerations for deploying AI infrastructure in industrial environments, including the importance of addressing size, weight and power constraints, as well as ensuring data security and remote manageability. I hope you enjoy this episode. Let's get started. Hello everyone and welcome back to Electronic Specify Insights. I'm pleased today to be joined by Matthias Huber, who is the Senior Director and Solutions Manager for IoT, Embedded and Edge Computing at Supermicro. So thanks very much for joining us, Matthias. How are you today?
It's bright and early in the day. Doing fine, thank you.
Excellent. Matthias, why don't you start by just introducing yourself and telling us a little bit about your background?
My pleasure. So I've been in the embedded edge IoT industry and actually my entire career. Started initially in R&D, then went to the US, opened a branch office for the company back then named Jumptech. And I've been with Contra for many years. I link a few, if you know those companies. And my roles have always been in product strategy and or customer facing roles, sales and marketing. So I've seen the entire progression of embedded PC modules, M2M IoT, Edge AI, the whole progression of, witnessed that over my time. So I've had a few cycles and now it's like Edge AI is super exciting. So that's the next frontier that we're working on.
Excellent. Yeah, it's certainly a very important topic for us here at the moment. And what about your role at Supermicro? Can you tell us a little bit more about the company?
So my role is what they call solutions management, which is basically intersection of product and sales facing internal functions. So in other companies that may be a single job function, we have product manager and solution manager, a bit inward outward facing. My group or part of the group is we're doing Edge IoT only within Supermicro. That practice is about 10, 12 years old by now. And we do products from small fanless, mid-size fanless, all the way to 3U rack mount servers. So we do a spectrum but everything's focused on Edge AI, and the footprints and so on. So the company is turning 32 this year. Still, our founder is still the CEO, which is rare at that size. Supermicro is a truly global company. So we have offices in the major geos in many countries. We produce in all three geographics, offer truly global service, which is for edge companies that's special. In IoT, that's an expectation. And the company went from motherboards to systems to what they call total IT solutions, which is systems with the necessary software. And since 12 years, Supermicro also has the embedded IoT group. Now we labeled it Edge. So we have the whole spectrum of products. And with the advent of AI, and AI as we know it really started, like, say, 3 years ago in that massive approach. So we see that now trickling from the big training systems and the data center system. It comes to the edge and it has various different shapes, how we see it showing up in the edge AI computing.
Fantastic. Thank you. And that sets us up nicely because this conversation is actually inspired by a recent white paper that was co-authored by Supermicro and NVIDIA, which explores how to accelerate the adoption of predictive and generative AI at the edge, and particularly in industries like manufacturing, healthcare, and retail. So for listeners who may not have come across this white paper, what was the motivation behind publishing it, and what message were you hoping to get across to industrial and embedded system stakeholders?
In Supermicro, see AI as the major change agent that's happening across almost every vertical market. So that influences the actions and outcomes for the business, the employees, the customers. Our motivation was to write this paper to bring light to that importance of edge in this AI transformation. Because everybody talks about AI, but AI on the edge is a bit of a different animal and has a bit of a different impact. So when we say edge, we mainly mean computing that's outside the data center, right? So, and once you're in the real world, especially as the manufacturing, there's a lot of other things that you have to consider, like, which sensors are you connecting, which cameras, where are you in the building, what power do you have, what temperature you have. So there's a lot of list of things to consider, but also how it's used, right? Because if are you interacting with an end user? Is a display involved? And et cetera, et cetera. And that local processing unlocks new functionality that were not there before, right? You can do things that were not possible. One example would be a digital concierge that, like in wayfinding in a hospital, you literally talk to the screen and the screen does this language processing, then uses a Gen AI to retrieve the answer, and then they have an avatar that moves and speaks back to you. Whereas this may sound a bit gimmicky, but if you think for like non-computer savvy people, this is the most natural interaction. But that requires a lot of compute, but it has to be local. Otherwise, you don't get the experience, meaning the data path to go to the cloud, gets processed in the clouds and back, is too slow to make a good interaction with the user. So we worked with our partner NVIDIA to write this white paper to show the importance of the requirements for edge, the edge AI adoption, particularly for industries and applications where the load time latency and the real-time processing and security are paramount.
Fantastic. And the white paper also talks about predictive and generative AI as two distinct but complementary halves. So how should industrial companies determine which approach or even a combination is right for their use case?
That's a super interesting one. The choice of predictive or generative AI or the need for both, this will always be depending on the application. So there's always, I hate to say it, but it depends. The Let's talk about how we differentiate those. The predictive AI, that's your analytic powerhouse. So that's your standard convolution models, that's your machine learning, time series analysis, it's all of that. So this is very good for like singular tasks, real time analysis when you have historical data patterns to work on. And that's what we typically think of when we talk about quality inspection, right? That's the go-to. The generative AI is, as we know it from the chat GPT and other systems like that, that's creating content. So that's, words in, words out. And that's usually shaped by human requests, or if you combine them together, then you get AI agents. We use large language models to synthesize this information. So how does it come together? As I mentioned just earlier, if you have more complex systems, then one of the elements or multiple may be Gen AI, especially when you do retrieval systems where you use existing data with a large language model to formulate an answer. And this, for example, could be thought of if you have a factory automation and you create an overlay. And instead of writing scripts and prompts writing database scripts, you just talk to your database system and it will produce an answer. That's the far goal. So in industrial companies, we'll have use cases where, as we just said, we use the predictive AI for the analysis, for the observational part, and then you can use cases with Gen AI for more advanced function, for more like an overlay, additional insights gathering. That's where those two combine nicely. And now recently, in the last few years, a thing that's kind of in between, because it used to be computer vision was very much in predictive, but now with the visual language model, there's basically something in between. You have a video stream, and by a prompt you can analyze it. So that is a whole new frontier, and that is now possible, and even on a small footprint. So you don't need to have a massive computer to run a VLM to analyze your video stream. So that advent of VLM it's almost at the stage where the innovation is faster than the adoption in the industry. So we now see things that are possible that at the start of your project you haven't even known about.
Mm.
So it's an interesting time to see how this very fast-paced innovation pushes into the industry.
Yeah, definitely. So, following on from that, what are some of the key infrastructure considerations that companies need to take into account when planning to implement edge AI, and especially in legacy or space constrained environments like manufacturing plants or hospitals?
Yeah. With infrastructure, it, it's all about the real world because when we say infrastructure, some people think more on the networking side, but to explain it from the built environment. So as an example, if you're like if you're in a factory, as you said, right, where what are you inspecting? If you do inspection, where is that object? Where's my camera? Where can I put the computer? Where does my power come from? Where do I send my data to? Is there a network? If there's a network, am I allowed to use it? How much bandwidth do I get? So there's a litany of questions that we have to consider for the infrastructure. Mainly, it's about north and southbound data connection, meaning southbound, that's your sensors, that's the input and outputs. How are those structured? Because as we go in the automation side, it becomes physical. So you have to, have this port and that feature and a CAN bus, and it has to match us to be able to physically connect, right? Northbound, that's then more on the network connection side, and then on the data integration side, like, what's the data formatting, what APIs can we use, things like that. And then in when there is no networking, there's still a few tricks to play. I mean, we can draw on, 5G technology, for example, and public 5G may not be the right answer. Wi-Fi can work, but it has its own issues. And that's why a lot of industry rolls out private 5G, so they have that ability to add things without having to pull wires, because pulling wires is hard, time consuming, and so on. So the one thing that's always a tricky one is the size and the compute you need, because oftentimes, for example, we're working with a customer, they make high-end machines and they only have a certain cavity inside their machine line for the compute. So the computer has to fit into that into that room, and that's it. And the power feed is limited. So we always have two parameters, and now you add a GPU or multiple thereof. So you have a bit of a higher power intake that you have to consider. And also part of the infrastructure then is how to choose the right GPU, CPU combination, or even multiple of the GPUs. And depending on size, we've seen different approaches. Like in the very low end, there's a couple of or a handful of specialty ASIC vendors that have established themselves. But once you get in the mid range, then you have like the smaller cards from NVIDIA, like the L4 or RTX 1000. Or if you go into the higher end, then we have the RTX 4000 or 6000 Pro line, which we use to build the higher end systems for the more advanced use cases where you have more data and more demanding models.
What about some of the challenges then? So the white paper highlights things such as swap constraints, environmental conditions, and data management at the edge. But in your opinion, which of these tends to be the most critical barrier in industrial AI adoption?
So we often talk about size, weight, and power swap. I add a C to that, swap C, because the cost is always a factor, right? So the if you look in the data center, there it's all about density and power efficiency, right? Pack as much compute as you can in a single rack and then make rows. On the edge, it's exactly the opposite. Everything has to be tuned, optimized to the task, to that size and budget. And oddly enough, it's the limiting factor is a different one. Like everything matters. Sure, it's a multivariate game, but there's one line you cannot cross this. It differs. Every use case has a bit of a different setup. For example, I just was talking to a startup and they said we need it wall mounted and it can't be more than 500 watts. And we want at least two GPUs. So package that. Then other mentioned customer and automation. They said you can only be, in a certain size and you have to have a 24-volt power input. So they give you that parameter. A different customer we're working on, they do image computation in the OR. and they have a noise issue. It's like it can't be over 60 dBA because if it's more, it'll be too loud for the OR and will not be accepted by the surgeons. So having said that, it's like the most critical item that is use case dependent, and you will work backwards from that. Because that's then, if that's the fixed limit, then you fold in the other parameters and work your way towards a solution, as mentioned with the power or noise or size. Oftentimes it's temperature, because if the system is inside a cabinet, you have, a box in a box, so you have higher heat buildup. Or, for example, in traffic management, the units are street side, they have sun exposures, and you have like temperatures up to 7 degrees Celsius as a requirement before you know it. As mentioned, to get the right CPU GPU combo, it's not exactly trivial. So that's what we have our solution managers for. That's part of what the job is, that we have the knowledge of what works, what doesn't. And we also have some of our architects constantly testing, benchmarking, and innovating to find good solutions. Because especially when you have multiple GPU cards, for example, in a dual CPU system, if you have a bank of four cards in one bank and you have NVL connection, is that the better choice? Or you have them in 2x2 attached to two separate CPUs? That has different impacts on the throughput and on the dynamics. And that's the base knowledge we use to make the decisions for build one route or build another route. And that's even that information I draw on my expert, because that's way beyond what I know. So, and last but not least, when we size a system, typically there needs to be headroom in the system. If the system serves multiple users, you need cache for that. Second, you want to keep some headroom for the future, that if you have another model coming that's larger, you want to have enough elbow room, meaning DRAM, in that system so it can hold up for a couple of iterations of your software, so you don't have to rip and replace it. The second large aspect is data management. What we mean by that is that the amount of data that's produced on the edge, it's impossible to store, and transport that. So to use cloud computing, sometimes it's possible, but you have latency issues and it costs money. You have to have the transport, meaning your ISP, you have to have cloud compute with an ingress and egress. And then there's GDPR issues that you may face depending on what your content is. So all of that makes it much more very straightforward to use edge compute, because then you use the data where it happens, because 95% or even 98% of the data does not need to be stored. Typically, customers store around the incident, especially in security, but also we do this in QA. So only small amounts are kept and then transported, uploaded later on for future model improvements. So you have a very reduced footprint, because as you multiply, there's not enough storage and bandwidth to handle this data offsite. Not even to speak of the latency, because then if you have to have millisecond control, you have to compute locally. So that pushes all the data back, or the compute back, to be on site right where it happens.
Okay, so following on from that, and a point you raised earlier, we know that generative AI at the edge requires both high compute power and memory. So how is Supermicro addressing these demands in form factors suitable for embedded or remote industrial deployments?
Generative AI requires relatively high compute and memory density, and I say that relatively on purpose because it's quite a spread. For example, a Llama 3.2 with a billion parameters, like 1.3 gigs, the 3 billion parameters, like 2.5. The visual versions are 5 and 90 billion, so that's about 55 gigabyte. So depending which model you pick, you can live in a few gigabytes, or you need north of 50 before you know it. So that's very critical, that to answer the question, you only have to know how you're going to solve your problem, like what models you're going to deploy. Do they have to all live on one card? Can they live on multiple cards? That's where the multi-card situation comes in, because then you parcel out what part of or which models sit on one card, second card, and what is the data flow, because that induces then peer-to-peer communication and latency. Now, we talked about size, weight, and power earlier. So we have different product lines, as said, from a small handheld device or size of a hand. Think of a romance novel at the supermarket. That's our smallest increment. That's our E100. It's a fanless box. There's also a air-cooled twin of that. Then we have the E300 line, and I say line on purpose because we refreshed it about every year with the latest and greatest CPUs. That is 25 by 21 by 4.5 centimeters, about a lunchbox, or just stack two laptops on top of each other. That's about the size. And once that's not enough, because these only can hold small GPUs, if you need more space, then we have our SYS E403. That is nicknamed the shoebox. It's about 30 by 22 by 9 centimeter. So it's sizable. It's not a big rack mount. So on those, we then can run your real-time image generation, speech recognition kiosks, and such. And we now have a new size of compute. Supermicro launched their first Jetson product mid-year, and that is based on the Orin NX Jetson. And that is in I call it IPC bricks. It's about 15 by 10 by 5 centimeters. So it's, not very large. And based on those, we can then pick and choose the physical size. Most of those systems have different CPU choices, so we can put in the right CPU, being Xeon D, Xeon SP, or an Intel Core, and size it up the right way. Once we go into higher performance, then we have systems. Then we in the 1U and 2U rack mount, but they're still short systems. They're still short servers. And then we can load them up with either two single wide cards, one double wide, or multiple thereof. So the top end is we can have one system can have up to 8 GPU cards. So this is very powerful, but that is for large Gen AI systems that we use. One thing to add to that is we talk about remote industrial deployments. So one thing that is crucial is remote management. And the systems are built for that, either with IPMI or with Intel AMT, to have access to the system even when it's not up. So as long as there's power, you have access, you can manage it. That is critical. And then there's two layers with NVIDIA's enterprise stack. One is the Triton Inference Server model, so that allows you to remotely update models to a fleet of system. And the second one is fleet management. There we can manage then everything from the OS up, all the different SDKs and applications that need to be loaded. You can then orchestrate with that tool. Because think of it, the company that orchestrates and manages that is not on site. It's even more extreme in retail. Like think of a fast food chain. They have, let's say, 2,000 stores around Europe, or 5,000. And each of them has one or two computers inside, and you need to update an application. So there's no way this can be done manual, because even the staff on site would not be able to perform that task. So it's done remotely, it's done uniformly, and it can be verified that way.
So what role would you say that your integration with NVIDIA software plays in helping customers accelerate from that proof of concept to production?
The software integration is critical. In the POC, it may not, companies see that when they go from the proof of concept to the first deployment. We have seen many, many struggles there, because what works in the small scale does not necessarily work on a bigger scale. So the key is that it's integrated, pre-tested, known to work, and using NVIDIA's software, then we can ensure a smooth rollout, meaning the scale out of the system then has a good chance, or has the highest chance of going smooth, because you cannot have, like when you build a POC, you don't have all the variables and you don't have all the variations in. And also sometimes you don't have all aspects live. So the full stack may sound a bit much. It may be overwhelming in the beginning. Do we need all this? The answer is not yet. So, and the full stack integration allows you to have a tested software stack from between NVIDIA and Supermicro. So it's known to work. It is an established system. as you scale out, there will be, very little wrinkles rather than having someone built this and it works on the first three machines, but then you go in the next environment and there's this, like, we've seen things failing left and right. Having the pre-tested software stack is like most reliable way to get there. And as mentioned earlier, we have the Triton inference server and the remote management, fleet management. Those are part of the stack, right? So that those interconnect, so that is already there, and that's the hardest part to get your POC work. That's one aspect, but to get the remote model management working, that's a whole different one. And this comes more or less pre-built. That gives you shorter time to value at scale. And that's the key point, is that once the POC is works, that we get to a scale deployment quickly and get to value quickly.
The white paper provides some compelling examples of edge AI in use. So what have we got? From automated quality inspection in manufacturing to AI-powered wayfinding in healthcare. Have you got any particular industrial cases that illustrate successful deployment?
So Supermicro Edge Systems powers several real-time inspections on production lines, and there's a couple of things to observe. So one is these are AI based. So with the visual inspection, computer vision, typically that is, configured, programmed, the traditional way. I mean, it started when I started my job, so this is not new. This is about Siemens is doing this for 30 years, right? But now with AI, it's a different approach that the explainability turns into a black box, but that is now, say, an accepted item. So that's one thing that happens. Second thing that happens, that also there always has been some elements that could not be automatically inspected. For example, in motherboard production, there was always the issue that the taller connectors, the through-hole connectors, could not was hard to get good automated inspection. Now they can do it. With AI, it's possible, and at the right speed, at the right accuracy. So we have these two layers that we replace things and we enable things that were not possible before. Basically, we have less humans in the loop. And by all that, so that's the visual inspection. That's just the QA item by item. And then you do the overlay. Then the predictive comes into play. And as we said earlier, it's like then you can connect the dots, you can roll in your time historic. And there's several applications that do that. And then you can see trends in your production. You see the the, the machine failure before it happens. So that's where you get your predictive maintenance element taken care of. And that reduces your downtime because you see the issues announcing themselves before they happen and you can work around that. And that also pushes down the quality control costs by about 10 to 20%. So most of the times it's small compact systems because they need to be near the equipment, near the camera, don't have too long of a cable run. So it's typically smaller systems installed very close to the inspection point, and then they are processing the video streams without needing cloud access. I just need a network to upload the data. So the AI helps to transform the process. I said earlier, right? You get the it's like classic inspection modernized, and then also you get updatable. That's also one thing that was not common in that context, that they could update their inspection model. It used to be a very, it's programmed, installed, and done and forgotten about for 10 years. Now there's a mindset of continuous updating. And so we have that, and you have these like the additional layers of information, the predictive, and then you can get even further to get additional insights and connect this information to other data sources. I mean, for example, in plastic production, the weather plays a role because it's air temperature and air humidity, therefore your machine settings has to be different. Now you can actually see those trends and patterns and steer that in. So the AI allows you to transform not just the individual. AI shows the transformation for the entire production quality process, showing real world revenue and impacting the company success.
Fantastic. And an important topic is obviously with AI deployments at the edge, data security and remote management are really key. So how are you addressing risks like data breaches and physical tampering and the need for remote orchestration?
I'll split it in two. So the first on the data side. So all these systems are built with TPM 2.0 by default. They all have secure boot and root of trust. And even we deploy self-encrypting drives, Opal compatible drives. Some of, depending, we can have self-erasing features. And all the systems have intrusion switches, so they can use tamper detection. And based on that, we can decide how to build the systems. Like what happens if, right, if the case has been opened during runtime, do you erase the drives? The action taken that is can be specified separately, but we have the mechanisms in place to secure and detect the. Since we have these installations with minimal IT support on site, right? That brings then in the remote orchestration, and we talked about the fleet commander, which takes care of that if you use the NVIDIA stack, that you have a software layer to load or unload your workloads, multiple thereof. But the remote orchestration is one element, right? If you go into, you also need to take care of your operating system, and we can take care of the firmware. We even have tools with IPMI that we can replace firmware of the system, of certain drives as necessary, especially when it comes to security patches. There's a way to roll those in to maintain that secure environment.
One final question before we wrap up then, Matthias, is I'm interested to hear how you see the edge AI infrastructure space evolving over the next 2 to 3 years.
Very interesting point. I just had a look at some of the material we used for the white paper, and that data source stated that the shift from experimentation to a cooperation with AI was at 11% in 23, 38 now, 25, and 68% in the next couple of years. So we already see it happening, right? We went from 10, 11% to 38, and basically the the use of AI will double, and analysts say that the value of AI at the edge will be about half of the rest of AI in total. So we expect explosive growth to come because in adoption, but also that will drive a demand for higher compute density. If you think back of the example of that interactive kiosk, there's quite a bit of horsepower in there to run all that on the edge. You could split some of that out and make a local data center if you have multiple kiosks, but still you have a dedicated system there. Then AI will move into more areas, right? Because right now it's happening in inspection, but it'll be in each machine on the floor. And then, as I mentioned earlier, the connecting the data for more insights that right now seems, high end. That will be an expectation in 5 years, right? Once it becomes a known practice, there will be an expectation from, it's like, the technologists, but also from the management, because they will get used to having these insights at their hands to steer the company. The far idea would be that it would, we see that now in experimentation stages, but to have retrieval augmented systems in use, to have your, it's like, private LLM, private Gen AI, but you have all your company data or relevant data in a database that you can use to formulate that answer. That way we can maintain data sovereignty for the corporation, data privacy, because we see in automation a lot of my data is my data. There's an aversion to the cloud because there's always something that could go wrong, right? In this case, you can have all that power of Gen AI, all the flexibility and all this like ease of interaction with your own data on top. We see that happening right now, still in concept phases. Large corporations use it for the internal work, so it hasn't found its way into the automation industry. But we can always see that happening. So there's a path to that. Will it be 3 years or 5 years? Your guess is as good as mine.
I think you're a bit more of an expert in this area than me, but thank you very much for your insights. And it's certainly an exciting space to be working in. And I think we've only really just started at the tip of the iceberg with this technology. So I'm looking forward to seeing where we can go with it. But yeah, thank you very much for joining me. It's been a pleasure having you as a guest, and I'm sure we'll get you back in a couple of years to see what else you've been working on.
Thank you for listening to this latest episode of Electronic Specifier Insights. Don't forget to subscribe to the series to keep up to date with our newest guests, and do share with fellow colleagues, friends and family who may be interested in the latest news from the electronics industry.